of noise? Yes. Okay. If there is too much noise, please make this way and you will feel comfortable. I don't like the noise of this system because it transforms the voice to some kind of unpleasant sound. Okay, so I need to see the result of your efforts to build the graph-directed system. Simplest graph-directed system, because I can explain you graph-directed system 100 times, but when you make it with your own hands, you will understand it 100 times better. You can study fractals theoretically, but if you make them with your own hands, then you understand them because you feel them. So did you write these operators? Who needs help? Yeah. You need help in typing the program? Two, yes, 2 to the power 1/2 divided by 1/4. I don't know what it must be. And it says any mistake?
Yeah.
Let us check. Oh, sorry. Apply. Line in block 30. Oh, yes, 1/4. Yes, 1/4, 3/4. You have a. You need to have a bracket, but you have a.
Oh yeah, third one.
Yes. No one knows where the danger comes from. You suppose that you made some mistaken formula, but it was what?
2 to the power half by 4, that only coming.
Yes, because there is one more closing, one. It is closed, but it was not opened. Yes?
No, that is for that one, no?
And by what is multiplied by this operator? This
Parenthesis for first one.
and no, 1/2 is applied to K1, but there is no K2. You see, you need to write star K2. Star K2, yes. K2. Let us check. Oh, again. Error at block. Escape. I will do one pretty thing. Okay. I just need to look at these letters. What is the reason for protesting? So this is 1/2. This is opening. This opens 1, opens 1, opens 2, opens 1, opens 2, opens 1, opens 2, opens 1, opens 2, opens 1, opens 0, opens 0, open. You see?
Okay.
So this is opens 0, opens 1, opens 0, opens -1. You have two two more closing parentheses, then it is needed. So you need to erase unnecessary parentheses. Counting parentheses, yes. Who needs help? Who needs assistance? Who can show me the result? Yes? And you have no laptop? Yes. It's not good from me. This is what? Very interesting. And K2. Yes. So can I read this editor? Because it should be analyzed. Sorry, I don't understand. No, you have macOS, but why? Yes. Not so much. Can you adapt the size so that I could see? No. This. User interface. It must be. Not that say. No. There is user interface and. No, this is not the way. Tools. No, Zoom box, no. We have user interface settings, and they are under this button. Yes. So, can you save all the results, close the program, and open it again? Yes. Oh, very good. And the second one? There are two objects, right? Yes, okay. That's very good. And did you succeed in building this?
No, sir.
Why? You errors?
Yeah, maybe some small mistake with the parenthesis steps. So
Yes. Because I was counting parentheses in one person here, and he had two more closing parentheses than opening ones. And you are making tiles, yes. Constructing tiles and analyzing tiles is main. Yes. What is? This can I enlarge it a little? Maybe this way, okay? To see the magnified result. So you need to make parentheses here. 2 to the power of 1/2. Yes, or please. 1/2 must be enclosed in parentheses, not square but round brackets.
This one?
Absolutely. Absolutely correct. Check. Again, because there are many problems with them. In this, yes, it says that problem is in this line. 1/2 multiplied by k1, and there must be union sign, right? K1 is small, right? Okay. 1/4 3/4 multiplied by rotation by 3 pi divided by ch, and you need to close.
This whole?
Not this all, but 3 pi divided by 4.
This
No, 3 pi divided by 4. This all, yes. Okay. Union 3 4 divided by 4. Rotation.
This one bracket is more here.
Yes, I don't see anything of that sort. Okay, let's check. Oh. 1 divided by 1. Union. Open. 1/4 3/4 close. Rotation 3 pi divided by 4 closed. And this opens, and when it closes, this parenthesis closes this one. Yes.
For this parenthesis.
Yes, this parenthesis is not used. Okay, and to what do you apply all this stuff? So you don't apply, you just write some letters and it's okay. They are not applied to anything. They are good by themselves. Close the star K2. Check. Whoa. Line in block 24, 1/2 K1. It's okay. 1/4 3/4. Rotation. Yes. So 1/4 3/4 multiplied by rotation. Close this. Close the parenthesis. Just in case. Yes. Just in case. Yes. And then open the parenthesis. And 3/4 1/4 rotation. And after rotation star. So no. Rotation, and then here you need to multiplication sign. Yes, 2 to the power divided by 4, and this. Oh, sorry. And where is the? You cannot open this one. Backspace. Sorry. No, return. Control Z. Yes, because I pressed wrong. You see, one. So K2 is this one union, this one union, this, and here you open the parenthesis.
The beginning?
Oh no, sorry. Excuse me, please. Union, then you have this one, and there must be some union between. Yes, but this union sign, this cannot be used there.
This one, no?
Yes, 3 4 1 4. So this union is applied to K2, so this bracket is opening here, and this is opening there. So make this one and this one to enclose this all this. Oh, no, sorry. First you begin here, parenthesis, yes, and second you close there.
Here.
All right. Now check. You didn't define pi. Pi equal to a sine of 1. Pi is 2 arcsines of 1, right? Here. Somewhere in the beginning. Here. Pi?
Use dollar sign.
No. Pi equal to 2 star a sine arcs sine, yes, of 1 no, of 1
OF.
in parentheses 1. Okay, apply. It works. You posed a lot of problems for me, yes. Very interesting. What is the problem? But it works.
No, this is not problem.
It doesn't say anything?
Yes.
Yes.
I'm not saying anything.
Yes. Doesn't say anything. First I need to... It's good, but not everything. Not all operators are listed.
K2 is coming, K1 is not coming, right?
K1 is not coming. So you need to look at K1. First you need to press this button and enlarge the picture. Enlarge it. Okay. And then enlarge this field. Okay. So K1 is not coming. K1 1/2 multiplied by K1 0 1/2 multiplied by K2.
Here multiply by K2.
Yes, of course. If you have K2, then there must be K2. Star K2, okay. Okay, and K2 is 1 multiplied by K1.
That's for K2, that will be...
No, this is not needed here. It is not needed here, yes. And do you think it's so? You open it, and close here.
Yeah.
It's okay?
Yeah.
It's okay?
Yeah.
Apply? Do you have K1? K1 is here, but it is not completely... Some operators are missing, and operators are missing in... Because here you have K2, but here you need to have K1 in. Here you need to have K1. So when you define K2, this is 1/2 multiplied by K1 and other things multiplied by K2. But when I see the K2, something is wrong. This is K2? Yes, because in K2 there should be K1, yes? And in K1 And what's about K1? But why K1 is such? K1 is very strange, you see? It must be a square. So find your missing. Are you okay?
Oh, no, sir. I tried.
What?
But it's something.
Identify. Please, please. Uh,
Yeah, I
It-
find it.
you found it, yes.
Getting this
What?
getting this type of vectors. So it is
You are not getting or getting?
getting it. This type of.
Yes.
Is it true or not?
Yes, it's true. Of course. Everything is okay. Yes.
If we so what is the rule of these values?
And these values are coordinates of these points. We have these 2 points are fixed and this point change the position. So
We can put any number over here.
you can put, no, you can put very large numbers because there will be no contractions. Because this value must be, its modulus must be, cannot exceed 1. It must be less than 1, yes. So if you have no contraction mappings, then you have problems. Oh, Vijay. What question? KA. KA, and here you have no KA2. No, right? Yes, you have no. Make star KA2.
But it will not.
2.
Okay.
Check.
No, I don't think it will work. Oh, sorry.
It's there is a computer engineer paradox. In our office, some computer was not working. So the computer engineer came, switched off, and it began to work. But when he went off, so he works only on its own errors. Okay? Who has questions? No, that's good, but not very good, because this is an unpredicted result. Oh, you may call. Yes, of course. If it's so, then I take my words back. Okay. So can we proceed further? We understood what are the graph-directed systems. Yes. There is one more interesting thing which I will not touch in detail. Maybe I will touch it in detail tomorrow, but not today. So, as I already said, very important condition is open set condition. Yes? So, if K is S1 of K union Sm of K, the system satisfies the open set condition if there is such an open set, all that it contains union Si of O, and if Si of O intersection Sj of O is empty if I is not equal to j. This condition guarantees that first that Hausdorff dimension of the fractal is the same as similarity dimension and is the same as a box dimension. All these dimensions coincide. So if we have a graph-directed system, we also need to formulate open set condition for graph-directed systems. The open set condition for graph-directed systems looks the following way. So, but we need to define graph-directed system. Yes? So if we have one space, then we have several maps sending this space to itself. Yes? But if we have two spaces, we have already several maps sending first space to itself, several maps which send second space, first space, yes? So suppose we have x1 and x2, two spaces, yes? And we write an equation, k1 is S1, 1 of K1 union S1, M, 1 of K1, right? So we have several maps which send K1 to itself, yes? And union S2, 1, S1 to 1 of K2 union S1 to M1 2 of K2, right? This way. And similar equation we have for the second copy. How can we imagine such a graph-directed system? So let us return to our example. We have very nice example. We have just two spaces and just 1, 2, 3, 4, 5, 7 maps, right? So we have K1. I will draw the picture. So we have S11. I can just so I have S1, S2, then map, this will be S3, this will be S4, just for simplicity. This will be S5, S6, and S7, right? There are maps. So what kind of equation we have? K1 is equal to S1 of K1 union S2 of K1, yes, and union S3 of K2, K2 union S4 of K2, yes, and similarly we have K2 is equal to S5 of K1 union S6 of K2, K2 and S7 of K2. You see, suppose we have many spaces and many maps. How to express all this? So we can, for example, in this case, we have two spaces, yes? First, and we have two maps from first space to itself, right? Then we have two maps from second space to the first space, right? Then we have one maps from the first space to second space, yes, and we have two maps from second space to itself. So we have a directed graph. So to express the relations between these components, it was invented by Malden and Williams in their paper. I can cite it and can put it. So this is called graph-directed system of maybe similarities or contraction maps, or simply a graph-directed system, and the attractor can be written as a system of equations. The system of equations. So in that case, we need to have several open sets. So if we have two components, we have the sets O1 and O2, and we have that S1 I of O1 intersection. So as how to write it? I need. Okay, so we have vertices of the graph, right? And we have edges. So each edge has its origin and its end. Yes? So we have that KU is union of SE of K. So if we have edge, then it has beginning and the end. So it will be alpha of E and omega of E. Yes? So it will be SE of K alpha of E, but U is equal to omega of E. So we express it in this way, and we can write very complicated graph-directed system in this manner. Yes. And in this case, we have a set of open, family of open set, OU, where U are all possible vertices, yes, and they must satisfy that union of SE, K, alpha, or O alpha, alpha of E, must lie in U O omega of E, and they need not intersect each other. So there is also, and in this case already, if the graph-directed system satisfies open set condition, then all the components of its attractor will have one more problem. We need to define the similarity dimension for a graph-directed system. Yes? And we need to define good graph-directed system. So the graph-directed system must be strongly connected. So this graph should be such that from any vertex to any vertex we have a path. So any vertices of this graph can be connected by a directed path. So I think we will discuss it later, because but I need to turn to my presentation because I was explaining this thing. So multi-zipper is the graph-directed system of similarities such that images of pairs of points corresponding to different components of this multizippers will be arranged in paths this way, and this will be a multizipper. So we can construct a multizipper whose components will look the following way. It's easy. It consists only of 1, 2, 3, 4, 5, 6 maps, which were 4 of them were defined in your programs, and 2 of them are not defined. You see? So consider so let us observe the time. Really, I don't understand what is the timing, and when we have a break. What? Today we finish at which time? 4:30. So we have 15 minutes, 20 minutes. Okay. 20 minutes. What can we do in 20 minutes? I can maybe I will not consider this example, but I will show you how to build dendrites. I must explain what is a dendrite. A dendrite is a continuum, locally connected continuum which does not contain closed simple closed curves. So a dendrite is an acyclic continuum. For example, what does it mean? For example, Sierpinski gasket is not a dendrite because it contains a cycle. Yes? If you have self-similar sets whose attractor is connected, then it is locally connected. Yes? So for self-similar set, this condition is satisfied automatically. If the space is connected, then the attractor is locally connected. You may ask me, is it possible to construct a continuum which has no closed curves but which is not locally connected? Understand, yes? If somebody can imagine that, please tell me. Yes. Okay, can you imagine a continuum without closed arcs inside it, which is not locally connected? Do you remember an example of a self-similar set which is not locally connected? Yes, it's a product of counter set and interval. But you can take this counter set, I will draw it schematically, take a point and draw lines connecting the points of counter set with this vertex. So you get a counter fan. Yes, you see? It doesn't contain any cycle, right? But it is not locally connected because you have infinite number of this rays which are approaching any of these points is accumulation points for the other. All the points are limit points, therefore a neighborhood of any point is homeomorphic to a product of counter set and interval. Yes? Okay. But this is not a self-similar set. Self-similar set can be of such nature. Yes? Self-similar sets, if they are connected, they are locally connected. So our problem will be to construct a locally connected self-similar sets without cycles. So there are some classical examples. First example was invented at the very first years of fractal geometry. It was invented by famous Hungarian mathematician Tamás Vicek, who has several thousands of citations of his works. Yes. So if we take 1, 2, 3, 4, 5 squares, then we get the Vicek set. And Vicek set will be a dendrite. How to prove that this is a dendrite? So I will tell you a dendrite criterion. Let K be a self-similar set. And let K satisfy the following properties. But this yellow wasp is still flying near the blackboard. Okay. Let K be a self-similar set. Which possesses single intersection property property, and let the intersection graph of K be a tree. Then K is a dendrite. You see? Very simple theorem, yes? But I need to explain what kind of intersection graph I keep in my mind, so that you could keep this notion in your minds too. So consider this Zwischek set. Yes, it has 5 copies, right? So we make a graph with 5 vertices, yes, but we will make a more detailed intersection graph, because each 2 copies intersect in 1 point, right? And we add this intersection point as the black points of this graph. And this graph is a tree, right? This graph is a tree. I don't understand what time limits I have today. So we finish today. Yes, I hope to prove this theorem today, but now I hope to prove this theorem tomorrow. And this is the most interesting. There are several interesting theorems which I wish to prove, and then K is a dendrite. Yes. And we will prove this theorem tomorrow. Yes, because this theorem considers the systems of continua which possess single intersection property. As you understand, if we have a dendrite whose copies intersect in 2 points, then this is not a dendrite, because there will be a loop. Yes. The only possibility for copies of dendrite to intersect, they can intersect in a line, or they can intersect in a subdendrite. At first, it seemed to me impossible how to draw a self-similar dendrite whose copy intersect in a subdendrite. But we succeeded in that. I will show you how it was made. Just file, open, can you wait for 2 minutes? Because I need to find this file. For that reason I need to feed my laptop, because it cannot wait for 2 minutes. Yes. File, store, open file, on. And then Unfortunately, I can't find this file without unswitching this. So, oh no, this doesn't work. And what is about that? I will show you one more very interesting example. Do you see the picture? This is an example of a dendrite, also a dendrite, whose copies intersect in a in this set. You see? Do you see this black set? You have 2 copies. One is this rose color and second is yellow. And they intersect in a set which is a cross. Yes. So, it's wonderful, but it is possible to construct for any kind of polygonal tree. It is possible to construct a dendrite whose copies intersect in this polygonal tree. Yes. This is a very good result, but it is still unpublished. It is still unpublished, and it will be, sorry, again it doesn't work. And this is also good. Yes, so we can intersect them in a tree, but I will explain how to make a dendrite which will intersect in a subdendrite. I cannot find this file in the time which is left to me, therefore I will explain you how to do this. And we will positively construct such a structure in closest days. For example, consider a dendrite which has 4 copies. This way. So I have some kind of a rectangle and also one rectangle 2 and a rectangle 2, and all these are images of this large rectangle. Yes, and the central rectangle is also here. Yes, so this will be a version of Wittek set. Yes, which slightly change when an elephant presses. So it can be extended to a dendrite constructed from hexagons, right? So you can draw 1 hexagon, then we can draw second hexagon, 1 more hexagon, and this hexagon. Yes? And imagine that there is a hexagon too. But we don't add this copy here, we have only these 2. And then we forget about this hexagon because we take this set and rotate it 2 times. Rotate it 2 times. So we'll have here 1 copy belonging to 1 hexagon, the other copy will belong to the other, and 1 copy belong to this hexagon. Yes? So we'll have two copies intersecting in such line. Intersecting in such line. But if you make different angles, we can have several copies intersecting in a subdendrite. And I will explain, I will explain it to you tomorrow, because now I have 1 minute, and this is my gift to you. This 1 minute is yours. So goodbye, see you tomorrow.